So this is Floriculture Nutrition, the latest in phosphorus fertility. My name is Josh Henry, and I'm a graduate student here at NC State. This is part one to this webinar, Plant Growth Response to Phosphorus. Now, we're going to be focusing on three different topics related to phosphorus nutrition. Part one, we'll be looking at the plant growth response to different phosphorus rates. Part two, we will look at color enhancement using low phosphorus fertilization. And in part three, we will look at a reproductive stage phosphorus deficiency. But for now, let's go ahead and get started with part one, growth response to phosphorus. Now, when you're looking at floriculture nutrition, you have to ask yourself, what are the key nutritional factors that influence plant growth? Here you can see that some of the main factors that you want to consider are the fertility rate, and specifically the rates of nitrogen, phosphorus, and potassium. These are some of the main elements that are going to be key to influencing your plant's growth. Here you can see a study that was done on Gerbera daisies using different rates of nitrogen. On the bottom, you can see the rates ranging from 50 to 400 parts per million nitrogen. And you can see that if you get to either side, either excessively high or excessively low, you get detrimental effects to growth. You can see that the plant that was grown with 50 parts per million phosphorus, or nitrogen, sorry, it was excessively small, as was the plant that was grown with 400 parts per million nitrogen. So the N rate and the type of nitrogen are both very important factors that affect plant growth. And when we're talking about the type of nitrogen, we're talking about nitrate, or NO3, versus ammoniacal nitrogen. So getting these ratios correct and having the correct rate and the correct type of nitrogen is, of course, very, very important for plant nutrition and plant growth. But also, the phosphorus fertilization rate has a significant impact on internode stretch. So phosphorus also plays a very important role in plant growth. And you can see on this Iresine plant at the bottom of the screen, you can see that it is exhibiting some high internode stretch due to very high rates of phosphorus. So you can see that section of the internode is very elongated, and it's not very attractive. It's not our goal in floriculture production to have leggy, stretched plants like this. And some of this initial research looking at phosphorus fertilization and internode stretch was conducted by Dr. Paul Nelson here at NC State back in 1992. And you can see there is a link to a magazine article from GPN magazine called What Really Causes Stretch. So if you're interested in seeing some of his work, you can follow that link and read that magazine article. And here is a picture, some of the results from some of his work looking at phosphate versus compactness in ornamental plug cuttings. So here on the bottom of the screen, you can see phosphate as a percent of nitrogen, the leftmost plant being grown with 50% rate of phosphate as the rate of nitrogen, and that would be supplied by a fertilizer such as 20-10-20. And as you work your way across to the right side of the slide, you can see that the rate of phosphate decreases down to no phosphate at all. And you can see that this has a very significant effect on the overall height and specifically the internode stretch of these plugs. And now, while we're on the topic of phosphate versus phosphorus, I just briefly want to go over some of the conversion factors. So common fertilizers provide phosphorus is phosphate, P2O5. However, my research reported here is in elemental phosphorus, so you need to know the conversions. Also, many other studies report in elemental phosphorus as well, so it's really good to not get these two confused. So if you have an elemental phosphorus value and you want to know what its phosphate value is, you have to multiply the elemental phosphorus value by 2.33, and that will give you the phosphate value. If you want to do it the other way, you can multiply the phosphate value by 0.43 to get elemental phosphorus. And just as a quick example, you can see if you were to mix a 20-10-20 fertilizer at 200 parts per million nitrogen, you would have 100 parts per million phosphate or 43 parts per million phosphorus. And that is, of course, because the fertilizer has 10% phosphate, which is equivalent to 100 parts per million phosphate, or if you multiply it by 0.43, 43 parts per million elemental phosphorus. Here you can see a chart or a graph of several different fertilizer types mixed at different rates of nitrogen along the x-axis and a corresponding phosphorus rate on the y-axis. You can see that the line on the top corresponds to a triple 20 fertilizer. And of course, if you were to mix that fertilizer at the highest rate shown on this graph of 200 parts per million nitrogen, you can see that this fertilizer would supply roughly 90 parts per million phosphorus. So of course, that's a very, very large amount of phosphorus you'd be supplying with this very high rate of phosphorus fertilizer. If you go down to the next line, you can see a 20-10-20 fertilizer, which would provide half of the phosphorus of the 20-20-20. 15-5-15 would, of course, supply a little bit less, and then 13-2-13, being a very low phosphorus fertilizer, would supply some of the lowest concentrations and lowest rates of phosphorus. So when we're talking about low phosphorus fertility, we're looking at how low phosphorus nutrition limits internode stretch, and it helps to keep plants compact. Now, this is very easy to implement for short-term crops like plugs, as we saw with Dr. Nelson's work previously. However, this is a little bit more difficult for long-term crops because we run the risk of running into phosphorus deficiency symptoms. And so during the last couple of years when I've been working with phosphorus, I've done a pretty extensive literature review and tried to find as many references to people using low phosphorus fertilization for their crops. And I found research that recommended rates of phosphorus anywhere from 0.01 to 10 parts per million for growth control of finished plants. So obviously that's a pretty big range. And 0.01 parts per million phosphorus is extremely low. This type of rate may work in natural soils, but it does not work in substrates. Part of the big problem with this is that some of these past studies use non-commercial substrates, such as phosphorus buffered clay. And now these clay particles do an excellent job of holding on to the phosphorus, and they make it so that you can very easily deliver phosphorus at a low rate throughout the entire production period. But unfortunately, this is not how most horticultural and floriculture substrates act with phosphorus. So this is not necessarily applicable to floriculture production. And if you were to use a rate as low as 0.01 parts per million phosphorus, you would very definitely see phosphorus deficiency symptoms in your crops. And so really briefly, just wanted to walk over some of the main phosphorus deficiency symptoms that you'll see. Here is a small New Guinea Impatiens plant with lower leaf purpling. This is one of the most typical phosphorus deficiency symptoms that you would encounter in your crops. So here you can see there's actually a number of things going on. It's not just the lower leaf purpling. There's a little bit of red coloration on some of those lower leaves, some lower leaf necrosis, and of course some very severe stunting. So this is kind of a good picture of what phosphorus deficiency tends to look like in most crops. Also, here is a slightly lesser known symptom of lower leaf olive green spots. So here is a poinsettia leaf that is displaying these olive green leaf spots within the central area of the leaf. And what we have found is that oftentimes when plants do not have that red or purple coloration that's typically associated with phosphorus, you get this chlorosis in the center of the leaf. And within the chlorotic region, you get these olive green leaf spots. So this symptom is not as well recognized, not as well understood, but it does tend to occur. So if you see these very defined little olive green leaf spots, that is quite possibly due to a phosphorus deficiency. So we were looking to optimize phosphorus, and our challenge was that soilless substrates have a low phosphorus holding capacity. So it's easy to go too low and run into phosphorus deficiency symptoms. So this poses a major question. When you're using commercial floriculture production practices, what phosphorus rates maximize growth, as you see in this picture right here? So we did a number of different experiments where we grew several different floriculture species with a range of phosphorus rates, holding all other nutrients constant. So for instance, we grew these plants with 150 parts per million nitrogen and potassium, and we ranged the phosphorus rate from 0 to 80 parts per million. At the end of each experiment, we measured the height, diameter, and dry mass of these plants and used them to determine an overall growth index. And here you can see the equation for growth index at the bottom of the screen, which was height plus diameter plus dry mass divided by 3. And so this growth index we used to give us a better overall picture of what the growth was like for each crop. And so here is one of the first studies that I did. This is Petunia Surprise Sky Blue. You can see that the plants were grown with a range of 0 to 80 parts per million phosphorus. You can see those rates on the bottom there. And you can see that, of course, the plants that were grown without phosphorus were extremely stunted. They didn't even reach floral maturation. But when you started giving the plants a little bit more phosphorus with just 1.25, the plants were a little bit bigger, still severely stunted, but they did flower. When you provided them with 2.5 parts per million phosphorus, they were yet again a little bit larger. 5 parts per million, still again larger. But after that point, you no longer really saw any significant increases in growth. And what I mean by this is that plants that were grown with 10 parts per million phosphorus were very similar in size to those grown with 20, 40, or 80 parts per million phosphorus. And again, if you look at these plants from the top view, you can see this trend occurring yet again, where the plants that were grown with 0 to 5 parts per million phosphorus on the top did increase with every increasing rate of phosphorus, but the plants that were grown with 10 to 80 parts per million phosphorus were all roughly the same size. So it appeared that growth was maximized with greater than 5, but less than 10 parts per million phosphorus. And our question was, how do we determine the optimal rate of phosphorus? And for this, we used regression analysis. So here you can see the mean growth index for each of the treatments we just looked at, all strewn across a graph. So growth index is there on the y-axis with the different phosphorus rates on the x-axis. And now what we would typically do in floriculture plant nutrition is we would fit this type of regression, this type of data with a quadratic regression model. And here you can see that it follows the data points fairly well. It could be better, but it typically follows the trend of rise and then fall. And from this model, we would determine that the optimal rate of phosphorus to reach maximum growth is about 48 parts per million. But of course, that's not really what we saw from the pictures, because if you follow this over to the actual growth index, that would indicate that plants grown with 48 parts per million phosphorus would be roughly twice the size of plants grown with 10 parts per million phosphorus. But this isn't what we saw from the pictures. So yeah, there's this almost doubling of growth indicated by this model. But what we saw from the actual plants is that those grown with 10 and 40 parts per million were about the same size. So obviously this type of regression didn't fit our data very well. So instead, we ended up borrowing a regression model from what they typically use for agronomic crops, such as corn and soybeans, and their response to nitrogen and other nutrients. And so this model is a quadratic plateau model. And how you develop a quadratic plateau model is by first following this very steep increase in the data points up to the point where the data plateaus. Pretty straightforward. You can see that if you follow these lines, you get a really nice regression curve that follows the data points quite well. And if you compare this quadratic plateau model with the regular quadratic regression model, you can see that with the quadratic plateau model, you reach maximum growth with 8.72 parts per million phosphorus, but with the quadratic regression model, you reach that with 48 parts per million phosphorus. So that's a very, very large difference between these two models. And we can tell that the quadratic plateau model definitely did fit what we visually saw in the experiment much better than the quadratic regression model. So this really emphasizes the importance of selecting the right statistical model for each species. And so for each species, we compared several different models, and it turned out that the quadratic plateau model usually provided the best fit. So again, the quadratic plateau model is like the one that you see at the bottom of the screen here, where it has a very steep increase at first up to a point where it then plateaus. And where it plateaus, you can use that to figure out where maximum growth was achieved. Now, really quickly, I just wanted to show you the foliar phosphorus concentrations from these petunias that we've just been looking at. And from the model, we saw that the plants reached maximum growth with about 9 parts per million phosphorus. But the odd thing is we saw very significant increases in foliar phosphorus concentrations past this point. And what I just wanted to show you here is that plants exhibit luxury consumption of phosphorus as well as other nutrients. So when you provide more phosphorus than they need, they aren't going to be necessarily larger in size or diameter, but they are going to take up a lot of that phosphorus. So this is just excess wasted phosphorus that you're applying to your crop. So now moving on, I just wanted to show you the results from a number of our different studies. Here is Petunia, Potunia neon, and you can see that it also followed a fairly similar trend where plants that were grown with either without phosphorus or with very low rates of phosphorus were extremely stunted, and it wasn't up until about 10 parts per million that you saw no significant increase in growth. And the plants that were grown with 10, 20, 40, and 80 parts per million were all fairly similar in size. And so after running the quadratic regression on this data, we found that the optimal phosphorus rate was, again, 9 parts per million. So after some of these initial studies, we initially went up to 80 parts per million, but then we realized that that was too high in most cases, and really we could find our optimal rates within the range of 0 to 20 parts per million phosphorus. So for the rest of the studies that I'm going to show, we only used rates of 0 to 20 parts per million phosphorus, and you can see those rates on the bottom here. So here is Cora, Burgundy, Vinca, and again, you can see this increasing trend in growth where plants that were not fertilized with any phosphorus were extremely stunted, very similar in size to where they were as a plug, so they really didn't grow hardly at all. But by providing just as little as 2.5 parts per million phosphorus, you saw a very significant increase in growth with the plant actually reaching floral maturation, though it was still somewhat stunted. And then you can see that with 5, 10, and 20 parts per million, it's getting more to a normal saleable size. And what we found here is that this cultivar of Vinca reached maximum growth with an optimal phosphorus concentration of 7 parts per million. Here we have Pure Beauty, red on pink, New Guinea Impatiens. And again, very similar trend. But here you can see that the model indicated that maximum growth was achieved with 12 parts per million phosphorus. So slightly different on this crop, still in that very low, around 5 to 10 part per million range, but a little on the higher end compared to what we've seen previously. Here's Angelonia, Sungelonia blue. And this one, again, like Petunias, plateaued at about 9 parts per million phosphorus. Here is Blazin rose, Iresine. This one, right around 7 parts per million. And again, as I mentioned earlier, this is one of those species that exhibits very significant internode stretch when you supply excess levels of phosphorus. So you can see those plants that were given 10 and 20 parts per million phosphorus had very, very long internodes compared to those that were grown with lower rates of phosphorus. And here is Partytime, Alternanthera. Again, you can see that these plants did quite well with very low rates of phosphorus. And in fact, this one reached its maximum growth potential at 4 parts per million phosphorus. So this is definitely one of the cultivars that we tested that was on the very low end of phosphorus requirements. But still, most of them are right around that 5 to 10 part per million range. And another thing that I wanted to express to you that we saw throughout all these studies is that not only does phosphorus have a very significant effect on the height, overall growth, but it also has a very significant effect on the leaf size. And as you increase your rate of phosphorus, you're going to increase leaf expansion. So again, by providing phosphorus rates in that kind of optimal range of 5 to 10 parts per million, you're going to achieve maximum leaf size as well as maximum height. But if you were to supply the plants with lower concentrations of phosphorus, you're going to have limited internode stretching, and you're also going to have limited leaf expansion. So what we saw from all of these studies is that 5 to 10, sometimes up to 15 parts per million resulted in maximum growth index values, depending on the species and depending on the cultivar. And at the same time, values of 2.5 parts per million phosphorus or less typically resulted in phosphorus deficiency symptoms. So here you can see the plant on the left provided with far too little phosphorus, the plant on the right supplied with too much. And what we were trying to find is that right balance of the optimal rate of phosphorus for each crop. So going back to this graph that shows the amount of phosphorus supplied by several different common fertilizers, we put our optimal range on this graph to show you what rates you would want to use of nitrogen from each of these fertilizers to achieve the right level of phosphorus. So again, starting with the line representing a 20-20 fertilizer, if you were to apply it at 35 parts per million nitrogen, you'd be right at that top part of the line. We'd be right at 15 parts per million phosphorus. So you can't really apply very much 20-20 without giving plants a very excessive amount of phosphorus. Of course, if you were to use a 20-10-20 fertilizer, you could apply double that rate of nitrogen at 70 parts per million. With 15-5-15, you could supply 105 parts per million nitrogen and still remain within that range of 5 to 15 parts per million. And then with a low phosphorus fertilizer, such as 13-2-13, you could easily go up to 200 parts per million without providing excessive levels of phosphorus. So in addition to these studies looking at optimal rates of phosphorus, we also did a couple of studies looking at growth control. So plant growth retardants, or PGRs, are the most commonly used method of growth control in floriculture production. However, there are a few concerns with PGRs, such as the fact that they're not labeled for all crops, and this is especially true for vegetable and edible growers who are limited on what chemical options they have available. So phosphorus restriction is a possible alternative way to control growth in greenhouse crops. So to test this experiment, we grew New Guinea impatient plants with phosphorus rates ranging again from 0 to 20 parts per million. And after several weeks, half of the plants were sprayed with paclobutrazol, while the other half of the plants remained untreated and were only receiving the different phosphorus rates. At the end of the experiment, we measured the height, diameter, and dry mass of these plants, and then we compared the maximum height of PGR-treated plants with the maximum height of untreated plants. So here you can see Tamarinda dark red New Guinea impatiens. The top plants were treated with paclobutrazol, and the bottom plants were treated without any PGR, but you can see the rate of phosphorus on the bottom there, ranging from 0 to 20 parts per million. And you can see that the plants that were sprayed with paclobutrazol were significantly more compact than those that were treated or that were not treated with a PGR. You can see that the leaf architecture is slightly different, especially if you look at the plants that were treated with 20 parts per million phosphorus. You can see that the leaves tend to go a little bit more out, not quite as upright as the plants that were not treated with a PGR. And of course, whether or not they were treated with a PGR, you still saw this phosphorus growth effect where plants that did not receive any phosphorus were extremely stunted, were displaying symptoms of phosphorus deficiency, and did not reach floral maturation. And that by providing just 2.5 to 5 parts per million, you were able to get a plant that did flower, but was still a little bit stunted, And then again, you get up to that 10 to 20 part per million range, and that's where you reach maximum growth. So what we found from this study is that plants that were treated with paclobutrazol and were given a higher rate of 20 parts per million phosphorus were similar in size to those plants that were not treated with a PGR and were given 5 parts per million phosphorus. And again, going back to those quadratic plateau models, here you can see there are 2 lines on this graph. The line on the top is representative of the height of plants that were not treated with a PGR. Again, these plants were taller. The bottom line represents the plants that were treated with a PGR. And you can see that the maximum growth, the plateau on that lower line, is in fact lower, indicating that if they were treated with a PGR, they had lower height. And so what we did here is we followed the plateau from the PGR treated plants to the point where it intersects with the plants that did not receive a PGR, and we followed that down to find what phosphorus rate would you could achieve similar levels of growth with. And as I just mentioned, plants that received 5 parts per million and no PGR were roughly the same as 20 parts per million with a PGR. And this model also indicates that it's right around that 4.5 to 5 part per million mark that you're going to achieve some level of growth control without the use of chemical PGRs. So our conclusions for part 1 are that depending on the species, 5 to 15 parts per million phosphorus typically resulted in maximum growth. 3 to 5 parts per million phosphorus, however, resulted in similar height for non-PGR treated plants as plants that received 20 parts per million phosphorus and a PGR application. So you could use rates in that very narrow range of 3 to 5 parts per million phosphorus to achieve some level of growth control without the negative side effects of phosphorus deficiency. And so low phosphorus fertilization can successfully control growth without negative issues of phosphorus deficiency symptoms occurring in your crops. And for more information, please check out our articles in the June and July 2017 editions of Grower Talks magazine. In June, we came out with the first article in the series called Go High or Go Low. You can see that on the left there. And in July, we released an article looking at growth control on the low, or using low phosphorus as an alternative to PGRs. So if you don't have physical copies, you can go to the Grower Talks website and you can go into their archive and download any of these articles if you want. So if you're interested in more information, I highly encourage you to go and read these articles, and hopefully they can help you learn more about low phosphorus fertilization. And with that, I'd like to end part 1 and open things up for some questions.